for joining us today. We're going to have a really good look at our calibration and a number of the topics that go along with that within the process of the entire manufacturing cycle. So with that, let's go ahead and get started. We've got quite a bit to go over, so let's jump right in. So we're looking at how we can create an effective torque management and calibration program within our process. And so when we look at what actually is the value of measuring torque, there are a number of good benefits, obviously, that we get from that. First, if we look at the overall ability just to analyze and see what's happening with our particular tools, this gives us really good assurance that things are working as planned. We can also take a look at what might be some of the root causes to some issues that we may be seeing. We can then take that data and analyze it and help us to move forward in the process. So as we test, we're gaining knowledge about our process and making sure that that is happening correctly. We can also make sure that we're documenting and all of our calibration activity that happens around our tools. We can make sure that all of the values and processes that are in place for the actual work are being documented with those specific tools and values. So this gives us a real good measure through either an ISO audit or some other materials where we may need to show show what's happening with our particular tools. So we can also then look at specific calibration data for a specific tool or a set of tools, and we have that ability to look at calibration cycles. Should we do the calibration based off of a time, a date, interval, or should we do it based off of cycles? So those are all good, valuable informations to have to make really good decisions about your tooling and your particular functions there. So when we look at some of the problems and issues that come up with torque, there are a number of them. Obviously, we want to make sure that all the fasteners are getting tightened correctly, but if they don't, we can see failures. And so if there are fasteners that are under torqued or not completed, obviously those aren't going to hold the parts together like it's designed to. We could have vibration and then the parts fail because there's movement allowed with the assembly. On the opposite of that is if a fastener is over torqued, then we can see certainly problems there where we may put a fastener or a joint past its yield point, and we'll take a look at that within this discussion a little bit later. But again, then we also have issues with the operators. But all in all, a very small fastening issue may end up resulting in a lost time, lost money, rework, and things like that. So if we can control, obviously, what's happening at the very start, then we can help to eliminate that type of waste within the process. So as we look at the different areas of torque, and when we're doing our measurement, oftentimes you'll hear a term, either a static torque or a dynamic torque. And so static torque is basically a measurement on a fastener that has already been assembled. Dynamic torque would be we're measuring as we are doing the fastening process. This also may come up when you're dealing with torque sensors. So static type of sensor does not have any movement in it. It will be a reaction style transducer. And then a dynamic will be a rotary type of sensor where you have the ability to actually measure while things are turning. And so that's kind of the difference between static torque and dynamic torque. And so that kind of leads us right into our poll question for today. So if we could have that question is, how do you measure your torque currently? Are you doing static tests? Are you doing dynamic tests? Or are you doing both? So we'll let that roll through here. All right, so within our poll question, we got quite a mixed response, but the primary answer was testing static torque, followed by both, and then finishing with dynamic torque. So thanks very much for participating in that. And so when we look at the different stages of measurement within the assembly process, there are basically three areas of manufacturing that we can do measuring for our tools and our torque. And so that's going to be prior to the assembly process, during the assembly process, and then after the assembly process. So when we look at prior to the assembly, we're looking at testing our tools to be able to set them up on a torque analyzer, so we can make sure that those tools are repeating correctly. We could also do tool capability studies for our R&D processes as well. So if we need to develop a torque specification, we would be doing measurement before that. During the assembly process, we can do torque verification and torque validation. And this would be where we are actually placing the transducer on the tool while it's in use, or bringing a calibration cart to the tool, checking it on the line, and then putting it right back in service. And then we can do the testing after the assembly has been completed. And this would be done with torque auditing, where we would actually look at fasteners that have already been assembled. And we could also do tool recalibration. And again, we'll touch on that here as we look at each particular area within the process. And so first we're looking at prior to assembly. And so we would be setting up our tools as we receive them. We can go ahead and put in or set the tool's desired torque value that is necessary for the operation. And so that can be done with preset hand tools. We can also do that with adjustable hand tools as well, and torque wrenches. And we can set those up with dynamic tools or power tools to make sure that those tools are repeating. And so one thing that can be somewhat confusing at times, we get this question, well, I've set my tool up on my torque analyzer. How do I know I'm getting that same value on my application? And the answer is you may be getting very close to that. It all depends on the joint characteristics between the torque analyzer, rundown adapter, or a joint simulator compared to your actual part. So it's good to be able to know exactly what's happening on your application with a transducer, and also setting that up on a torque analyzer and understand the correlation between the two, so you can be as accurate as possible. And so that's how we would work during the tool setup process with measuring the torque. If we look at the different types of tools we would use with that, would be a torque analyzer with an internal transducer. We could also use a different type of tester where we can actually add additional torque sensors to that, or we could use that for hand tools. We could also use that for power tools. And here's an example of the tool with a rundown adapter on it to help simulate the actual rundown of the part. And so this is just the example of ways that we can use the torque analyzers to help set up our tools and make sure that they are producing repeatable results within the torque tolerance that we may need. So when we look at being able to develop a torque specification through R&D, this is quite a unique process, but it is something that may be very helpful in certain situations where you may be seeing problems or errors or issues with a particular joint or a particular fastening operation. And so oftentimes we'll get a inquiry that they're having, a customer may be having issues with this, and how can we help do that? And so if we look at using basically a yield distribution, we can help to look at what that problem is. And so if we took a fastener on a joint and we ran that all the way up to the yield point, or where that fastener is going to fail, and we can then determine what the proof load is going to be for that particular fastener on that particular joint. And so everything in the lower left of the graph there is all of the elastic region of the fastener. And so at any point, if we were to back that fastener out, that fastener would then relax and come back to its original shape. However, if we go past the yield point, then that fastener will get into the plastic region, and it will then be permanently deformed. And so typically when we run a fastener to destruction, we can then take a look on our analyzer and see what that value is, and we can reduce that from to about either 75% to 85% of the destruction point. If you want to go from the yield point, then you could be looking at a value of 85 to 90% of the yield point. But within that spectrum is where you're going to be able to get the maximum clamp force from your fastener. And so when we say what is the clamp force, if we take a look at this animation, we've got a bolted joint with two pieces that we're trying to hold together, and as we tighten the nut, the fastener inside is stretching, creating the clamp force to keep the two parts together. So the fastener itself is acting much like a spring to make that type of correlation, but obviously that particular job of that fastener is to make sure that those parts don't move and they stay where they're supposed to. So if we take a look at what would happen if we did go past that, if we remove the fastener and the nut, we see that the bolt goes back to its original shape. However, if we were to then remove the material and we saw that the bolt has now been elongated, then we have permanent deformation, and that particular fastener has gone past the yield point. And so and that's very important, because if your torque values are right around the yield point and you go over it, any type of shock or vibration to that fastener could cause that bolt to break, or the fastener to come out of its location based on either the strength of the fastener itself or the strength of the material that it's in. And so that is how we can do testing to make sure that our torque values that we're calling for are what we need. Because the goal here is the clamp force and making sure that we have the right tension, and the torque is the means to be able to achieve that tension within the fastener. So let's take a look at the type of testing we can do during the assembly process to help ensure that we are getting the right torque values. And that can be done through the torque verification or torque validation process. And so what is going to be the most accurate way for us to do this testing is by the use of a rotary sensor and being able to put that in between our application and our tool, and this is going to give us the actual torque that's being delivered onto the part, which is exactly what we want to see. So by this use, periodically we can not only confirm that the tool is performing correctly, but we are also delivering the torque value that we need for the part. Another way we can do the validation is by using a torque analyzer and periodically coming through and testing the tools on the line to make sure that they are performing repeatably on the torque analyzer. So there is a little bit of difference there. When we use the rotary sensor, we are actually getting the torque value that we are getting on our part. When we use a torque analyzer, we are getting a torque reading that we are double checking to make sure that that is repeatable. But the joint characteristics between the rundown adapter that we may be using on the analyzer versus the actual part may be slightly different. And so that's a consideration to think of. So those are the ways that we can do some testing during the application. So let's take a look at what we would be doing after the assembly process and what types of tests we can perform at this point. And so with the after or torque auditing process, we can do tests like a first movement test. We can do a loosen test. We also can do a marking test. And all of these kind of may fall under the term of residual torque that you may hear when you're doing some torque auditing after the fact. And so the first movement test is where we actually take the fastener and we will turn it in the assembly direction. In most cases clockwise. We're going to turn that a few degrees to see what that torque value is. And in this case, we would be using either a torque and angle style wrench with the ability or with a built-in transducer, or we would be using a rotary type sensor to see what that value is when we turn the fastener a few degrees. And so that would be the first movement test. The loosening test would give us a value once we break away that fastener. So we actually will take it in the loosening or counterclock direction and see what that value is. Then we can also do the marking test, where we would draw a line on the fastener and then also on the assembly, break that fastener loose, and then bring those two lines back together, and we would measure what that torque value is at that point. And so all of that again kind of encompasses the ability of residual torque. The values that we would be seeing in this point are going to be somewhat close to the actual torque value that was delivered, but because of there are a tremendous amount of factors that go into the actual torquing during the process, that value is going to be different due to facts of lubrication, could be speed, the type of tool that was used. So a lot of those variables that go into the actual delivery of the torque value are going to be a little bit different than what we would see during the test. And so by doing a number of different tests within whatever torque auditing process you might want to do, at that point you would be developing a little bit of a uncertainty process of the values that you see when you do the auditing compared to the values that are during the actual process. And so you can develop a correlation between those two to verify if you are getting the correct torque value. And so one other fact on residual torque that that is somewhat notable is that if once we remove the tool from the application, there is no more torque in the fastener. So this is basically the tension that is left. Now there is a slight bit of torque that may be present because of the torsion that is in the fastener itself, but for us to be able to measure the torque, we actually need to get that fastener moving again to be able to excuse me, measure what that torque is. So that's just a little note on residual torque. So let's go ahead and we can look at a couple different animations that will display kind of what we're looking at. And so in this case, in the first movement test, we are just turning the fastener in the tightening direction just a few degrees to see what the torque value is that we are seeing. And that's going to be very close to the value that it was originally torqued at. But sometimes you may see an initial spike in torque and then a drop for the first few degrees of rotation because in order for us to get the fastener moving again, we actually need to create a little bit more torque. But once it starts moving again, we have from about 3 to 5, sometimes to 10 degrees of movement to see what that initial torque value is. And then from there, again, we can develop some type of correlation to what the tool is set at, what it is performing at, and what output we are getting with the test. And that measure of uncertainty will give us the ability to do that correlation to what that value is. For the loosen test, we would simply just move the fastener and break it loose and see what that torque value is. And again, that would be a correlation to the joint characteristics, and if we are constantly seeing the same type of value, then we can conclude that the torque that we're applying here and this loosening is correct, and we are getting what we are looking for. The last one that we'll be looking at is the marking test. So if we again mark the part and the fastener, and then we go ahead and we will break the fastener loose, and then we then come back and retighten it, that will give us a very similar torque value to what the fastener was initially torqued at, minus any changes in the coefficient of friction based off of materials, could be based off any lubrication that was used. And so that coefficient of friction may change depending on the materials. For example, you may have a coefficient of friction over 1 when you've got 2 aluminum parts because there'll actually be adhesion that happens when those parts come together. So it just depends a lot on the material. But again, you want to be able to develop what the correlation is between the values that you're seeing and the values that your tools are producing. So if we go ahead and look at this demo-wise, we can take a look at what I have here. So I have a thread block with a few fasteners on it. I have our torque analyzer here. I also have one of our rotary torque sensors with just a static screwdriver on the end of it. So we can measure inline. And then I've got the same thing that we can do some measurement with, and that would be the use of a dial screwdriver. So you have a little bit of a lower tech version versus a digital version. So that is the equipment that I've got set up here. I also have a torque screwdriver, and we'll go ahead and run some fasteners down. We'll do the different tests just to show you how those different tests function. So let's go ahead and run some fasteners down first. Power this on, and if we set our preset here to 1, we can go ahead and run these fasteners down to, it's about 18 inch-pounds or so on these first 4. And let's move this here so you can see that a little bit better. And so I have the rotary sensor hooked up to our analyzer, and then we'll go ahead and run these fasteners down. And so we have those readings here. And so with this, I have these four fasteners. Three of them are kind of simulating a more hard joint, and then the last one is simulating a softer joint where we have a washer and then a gasket as well. This is so we can do the first movement test. It's very difficult to do the first movement test on a really hard joint because of the fact that you have a lot of friction to overcome, so it can be very, very difficult. In this case, I will do the first movement test on the softer joint. This will allow us to be able to see what's happening, and we can see with the test where we're at. So let me go ahead and clear that. I'm going to remove the screwdriver, and then I will put on just a static wrench. And in this case, we're going to look for the fastener to move just a few degrees of rotation. And so once we see that, we can go ahead and see where we are on our analyzer and what that value might be. And so as we're applying load, we get a few degrees of rotation, and you can see that because of the joint relaxation that we are seeing here, we're torqued it to about 17 or so inch-pounds. But when I do up my first movement test, you can see we're at just over 10 inch-pounds. So there's quite a bit of relaxation that's happening from when the tool shuts off because of the softer type of joint that we see here. And this is the results from that particular first movement. Because we are turning the fastener in the tightening direction. Next, if we want to go ahead and do a breakaway torque, we can sample that with these three fasteners, and that would be put us in the what would be a negative number on the display, because we're actually running it in the opposite direction. And so as we do that, and I'll turn the until we get that loose, and you can see we're at 13, and we may see the torque increase based off of the different fasteners that I have here. Yep, 16. And 17. So because I use this quite often, these particular fasteners do get a lot of work, and a little bit of galling can happen, but I've noticed that some of these fasteners tend to produce a little bit more torque that way. So that's how we would do our breakaway test. Now the last test would be the marking test, and let's go ahead and do that. We'll set the tool again. And let me just make an adjustment to which preset I'm using. That way, with the dial screwdriver that I have, this will allow us to be able to see what that value is. Actually, let's go ahead and use our same value just to make it a little bit more consistent. Okay, so we'll go ahead and run this down. All right, now we can go ahead and do our marking test. All right, so initially we'll go ahead and we will break that loose in the reverse direction. Then we'll go ahead and realign those two segments together and see what values we get. So again, our breakaway, very similar on this particular fastener. And then when we bring this line together, there we go. And so again, depending on the different characteristics of the particular joint, this is a way for us to be able to develop, again, a correlation between what we are seeing when the tool is performing to what we see when we test. And we could develop parameters so that if we are doing our after audit or after assembly audits, we can make sure that a value that we may see that may be different from the actual value that was produced is still within an acceptable limit based off of sample data that has been taken. And so it's very difficult to measure a fastener that has already been torqued, because a lot of the factors that we mentioned that go into actually creating that clamp force and being able to reproduce that when you're trying to test something that has already been done makes it a little bit challenging. But there are ways that we can do that as well. For some of the higher torque values, you could do it with a digital wrench that may have a torque and angle sensor within it. And that way you can just set your angle, turn your fastener to anywhere from 5 to 10 degrees and see what value you get that way. We also have rotary style sensors that have an angle in them as well, so you're able to see what those values are at a specific angle using that type of sensor. And finally, we have the last facet of our discussion, and that is torque calibration. And so this is the process of being able to test our tools to a higher standard to make sure that they are being repeatable and accurate with their torque delivery. Now, this can be done on a number of different cycles that can be presented. It can be done either every 6 months or every 12 months or whatever the process you have for your particular organization. We do have customers, however, that will be testing their tools on a certified and traceable calibrated analyzer. And so every time they do a test on that particular tool, those results are traceable to that particular torque analyzer. And so they test their tools periodically, and as long as the tools are performing correctly, they will not send those tools in for calibration or recertification until they start showing signs of moving out of the calibration for that particular tool. So there is a time-based type of calibration, and then there's performance-based type of calibration. Depending on what your organization feels comfortable doing, there are definitely advantages to moving to a performance-based type of calibration. There just is a lot of testing that needs to be done for that as well. And so that's going to leave us or bring us to the conclusion of today's discussion, and we'll go ahead and look at the questions and answers we have. And so, Chris, do we have any questions?
All right, Dave, thanks. Yeah, we have a couple questions to kick it off. In the fastener destruction process to determine the torque spec, is there a recommended number of screws that should be tested to determine that torque spec?
Yeah, it just depends on the part and the ability to go ahead and make those tests. And if you can do as many as you can do is going to give you the best results. But if this component may be a very expensive piece of machinery or damaging, that will be a considerable loss. Then you may need to just do just a couple. So it really depends on the amount of comfort that you have in doing that destructive test.
All right, thanks, Dave. Next question was, when you measure the dynamic torque, what items can influence the torque on the fastening joint besides the soft gasket that you had shown?
So you have quite a number of different variables that can go into producing the final torque that is given. So not only is the gasket one of those influencers, you have if there's any lubrication involved, is it the fastener lubricated with Loctite or with oil or anything like that, that's going to change the coefficient of friction. You're going to get a much greater clamp force at the same torque value for that particular fastener. You have the actual material that you're using. Is it stainless steel? Is it aluminum fasteners? Is it a cutting thread type of application? All of those, again, are going to play a part in the coefficient of friction that is the majority of the torquing force that we see. And then the last variable is going to be speed. If we're using a very fast air tool at, say, 1500 RPMs compared to a direct current tool that may be operating at 300 RPMs, we're going to see a much greater different torque value than you would be between the two. So those different variables can play a part. The last variable, which is a big one, is the operator as well, can create influence on that, especially if they're using a click style wrench. You may have an operator that thinks that the tighter the better, so I'm going to triple click that click wrench, and by doing that, they could be adding up to double to 3 times the amount of torque that's needed or called out for that specific fastener. So there is quite a number of variables that go into the actual torque output, and the more you can control those variables, the more accurate you're going to be.
All right, thanks, Dave. Next question was, how frequent should a torque audit process event take place for an application?
Again, that's going to be determined by your internal processes. If you want to do that, once a month, once every 2 weeks, or weekly or daily. Again, it just depends on how accurate you need your process to be. And by doing the auditing, you are validating your process. So there may be vendor requirements that you may be building a subcomponent for a part, and they may need that type of information. So it's going to be dependent on the internal process and what the actual specification is for you or your customer.
All right, thanks, Dave. Last question looks like is the torque verification process something that you recommend like monthly or weekly on a tool, or even a shorter interval?
Yeah, again, it will depend on how joint critical that particular tool is being used for. So we have customers that will validate their tools. They validate them once a month, or once a week, or once a shift. It could be the operator comes in the morning, they test their tool, make sure that things are working correctly. Then they go ahead and put those tools in service. And then we have, for those very delicate and very crucial life type of applications where if something went wrong, bad things could happen. They may again test their tools before it's even used and document what those results are before they do work on the part, and they may even test it after work on that part. So again, it just depends on what type of validation you want for your process, what type of records that you may need for that, and how well you want to validate your entire manufacturing process.
All right, great, Dave. Looks like that was the last of our questions.
All right. Well, I want to say thank you very much for joining us today, and I look forward to our next installment. And again, thanks very much, and have a great day.